Okay. Uh, Thanks everyone for coming. We're very happy to have Tim Cohen here. Tim is an expert in effective field theory, among other things. And I think I've already mentioned a few times his fantastic set of lecture notes on the topic. So it's a treat to have him here to tell us about a very interesting sounding effective theory. Um, Take it away, Tim.
Great. Thanks, Seth. Thanks, everybody, for coming. Yeah, I'm really excited to be here. Of course, prefer to have actually traveled to Chicago. I had a Chicagoland plan that was coming together that was supposed to happen in September this year, and might have seen all of you in person, but this is better than nothing. And yeah, so I was also remembering, I think the last time I was at U Chicago to give a talk was back when I was collaborating with Mikhail Salone and Richard Hill and Martin Bauer, where actually I learned a lot of the techniques from that collaboration that have fed into all this future work. So anyway, it's kind of fun for me to present this, which is arguably a genesis of my time interacting with great people at Chicago. Cool. So I want to tell you today about a new effective theory description of the soft limit for modes in de Sitter space. And this is in collaboration with Dan Green, who's the actual expert here. Basically how this came about was Dan came and visited us at Oregon and gave a great talk. And then afterwards we were talking about IR divergences in de Sitter, and just, Dan was giving me a rundown of what the structure is, what's known, and so on. And we realized that there was a very kind of obvious expansion that one should be able to do, namely this expansion here that I'll describe in a lot of detail throughout the talk, and that there ought to be a nice modern effective field theory description in this limit, in this long wavelength limit. And so it took us a little over a year to figure it out, but I think we've now formalized how one should think about, or not the only way, but a very useful way to think about the long wavelength modes in de Sitter. And I know there's a huge variety of expertise here, so my plan is to keep things kind of top level. I'm available after the talk for at least an hour, if not longer, and so any technical details that people would like to hear about, I'm happy to stick around and kind of go through some of the slides I'm sure I'll skip in more detail. And the paper's on the archive, and we tried to make it super accessible. There's lots of detail there, so you can also go look there. Okay, so let's take some time to just set the stage. What's the physical picture we're talking about here? And the study of long wavelength modes in de Sitter is actually quite an important physical problem for our universe because of the story of inflation, right? So we all learned this kind of cartoon in kindergarten about modes being produced during inflation. So those would be these UV modes here. And then they get stretched out by the exponential expansion of a near de Sitter background during inflation, right? A quasi de Sitter background. And those modes get stretched beyond the horizon. Those are the modes that we're going to be able to describe in this effective field theory. And inflation ends, the scale factor scaling changes, right? And eventually those modes come back in and they seed structure. So systematically understanding the quantum field theory that generates those long wavelength modes is deeply tied to the history of our universe and even how we got here. And it's really all about the long wavelength limit. So understanding the infrared of these theories is important and interesting. And for practitioners, there's been a formalism, largely developed by Weinberg and by Maldacena, the formalism that's known as in perturbation theory. And one aspect of in perturbation theory is that the physical dependence of quantities is quite obscure until you get to the final answer. And so one really nice thing that happens in this effective field theory is that we're able to introduce a so-called power counting parameter that organizes an operator expansion. And that power counting parameter makes the physical properties, in particular, the time dependence or the scale factor dependence of quantities, manifest essentially at every step of the calculation. So there's a real conceptual advantage here to just the brute force way that a lot of these calculations have been done in the past. Okay, so let's talk a little bit more about the infrared of QFT and DeSitter. So I'm a huge fan of effective field theory techniques because, especially in the modern way of thinking about things, so-called continuum EFT, because there's this real conceptual advantage, which is that by reorganizing the degrees of freedom, you have some UV modes, which may look very different in the IR. And through that reorganization, you learn what the real propagating modes look like. And so we're going to see that happen here. We're going to ask this question as we take the long wavelength limit, what are the degrees of freedom that emerge? Okay, so I'll make that very concrete. And there will be a mapping between a UV scalar field and these IR modes, which are the objects that appear in the EFT Lagrangian. Then beyond that, once you have the modes, you want to know what symmetries persist. What are the what's the dynamics, right? What does the propagator look like? And what is the sort of naive free theory of these modes look like? And as we'll see, it's a little bit different. Going from the UV to the IR, there's kind of a transition in the kinetic terms already. And so we'll see that the Lagrangian and the dynamics are quite different in the IR. And in particle physics, we're very used to defining our theories in terms of symmetries. And that really, again, is fundamentally because effective field theory works. And so this question of what symmetries persist in the IR will also be something we can address. And so we can really understand what are the rules. And the symmetries, of course, then provide us with a way to build operators, right, consistent with those symmetries. They provide us with a way to constrain observables. And as I'll mention in the next slide, there's some profound consequences just from knowing what the symmetries are. That's unsurprising to anyone who's done anything in QFT, right? That's pretty typical. Once you know what the symmetries are, you often can immediately tell whether or not certain terms are allowed, which tells you a lot about the dynamics. Okay. Then there's a bit more practical, I mean, this division, of course, is arbitrary, but there's some more practical concepts here, which are by writing down an EFT description, and especially by having a well-defined power counting, we can organize an operator expansion. And again, that gives us a lot of insight into what dominates the physics, okay? And as we'll see, depending on the limit, the relationship essentially between the mass and the Hubble scale, the mass of this scalar field that's living in this DeSitter background, we get very different operator structure. Our power counting changes dramatically, and it leads to quite profoundly different consequences for the long wavelength physics. So massive fields are going to behave very differently from massless ones. And, we're all kind of familiar with this already. Massive fields are just going to decay quickly. So at late times where we're going to evaluate correlation functions, we're going to see that there's essentially no contribution from massive fields, although we can still in detail check the quantum properties in the effective theory match calculations that have been done in the full theory. So that's a nice test of the formalism, but at some level, nothing interesting happens. Just like the W boson's influence falls off as an exponential of minus MW, right? The same thing happens here. When you go to the massless limit, now you can get large quantum fluctuations sourced by Hubble. And so we'll see how that emerges, how we can describe that in the effective field theory formalism. And it's really going to be a consequence of power counting. We'll see that the theory takes quite a different form in the mass as the mass approaches zero. Okay. There are other practical, important practical uses of the EFT, namely to do with dealing with divergent integrals. So One of the difficulties in working with this in perturbation theory formalism is dealing with divergences. And I should probably say a few words, right? What we're going to ultimately be interested in doing is we're calculating correlation functions that are projected along a horizon at future infinity. And so, so we're going to be doing integrals over momentum modes, and those are going to be independent of integrals over time. That's because we're in this de Sitter background, and we have essentially broken the relation between time and space. If you like, we've picked a frame, and we'll work here in a particular frame. And then once we're there, we can project onto future infinity and ask about correlations between momentum modes. Okay. And in doing that, when you actually go and you try to apply Weinberg's formalism in the full theory, you find that depending on the order you do integrals, divergences appear. There's a very complicated mixing of divergences that look like maybe they're due to the time integration or due to the momentum integration. And so it's actually quite confusing to isolate these divergences. Furthermore, essentially all attempts to regulate these divergences rely on using a hard cutoff. And we all know that hard cutoffs break symmetries, and that's also true in de Sitter, okay? So one of the things that we're going to be able to do here is we're going to be able to invent a regulator that plays very nicely with the effective field theory and lets us use something that looks like dimensional regularization so that we can maintain the symmetries at every step in the calculation, okay? And this is just like with dimreg in normal QFT, right? This provides us with all the same benefits. And in particular, it lets us really apply the philosophy and then the techniques of continuum EFT, which rely on scaleless integrals vanishing. Okay, so we're going to be able to play the same tricks here, where we can essentially integrate momentum modes from 0 to infinity, even though we've integrated out UV physics, because we have expanded away the UV contributions using the so-called method of regions or something that looks like it. And so we can do these integrals all the way to infinity and only capture the IR dynamics, just like in other examples like HQET, or even the way that we calculate using dimreg in the standard model. Okay, and then finally, there's the advantage that we're going to be able to, again, use the standard continuum EFT formalism to trade what look like IR logs in the UV theory for UV logs in the effective theory. And once we have UV logs, then we can apply renormalization group techniques to sum those UV logs in the effective theory, which is essentially summing IR logs in the full theory. And so we're going to be able to play the same tricks here, and we're going to be able to systematically sum IR logs. Again, once you've set up the theory, you don't have to be clever anymore, you just calculate, okay? Great. So are there any questions or comments? And I should also say, please jump in and bug me with questions along the way if anything comes up.
Yeah, so one issue is that sometimes people, claim unphysical things by using this sort of dimensional regularization to sweep various divergences under the rug. Mm-hmm. Like, for instance, claiming that, we don't have to worry about quadratically divergent masses, because I can just define them to be zero in dimensional regularization. Mm-hmm. That hides a lot of physics of, naturalness and things like that. So I was wondering which of the divergences you're going to be encountering suffer that issue.
Great. Yeah, that's an excellent question. So so I would argue that certainly in that example that you gave, right, the way in which those divergences get hidden is restored in the continuum EFT, from the continuum EFT perspective, by properly matching the full theory onto the effective theory, right? So if you integrate out a heavy threshold and you do it correctly, then you're going to see that quadratic divergent contribution to the mass appear from matching. And so if you like, the same thing is going to happen here. We're going to be able to perturbatively match between the UV theory and the EFT. And so any of those kinds of effects that are due to integrating out momentum modes and the way they contribute to relevant operators are all going to be captured. But even more than that, we're going to see that there's only a very special case where we even get any relevant operators besides the propagator. And so really, we're going to only get log divergences and then power suppressed corrections in the EFT. And those, I think, there's significantly less worry that you might be missing something. But I probably won't get into these details, but we did a number of consistency checks against calculations that are already been done within the context of the full theory to make sure that we were getting all the right logarithms. So that's really the focus here, is that we can capture all of the logarithms and then in the case when we need to systematically resum them.
Okay, thanks.
Yeah, thank you. Great. Okay, so I've said this basically already, but so what we're trying to do here is we want to expose late time behavior, long wavelength behavior. Okay, so those are the limits we're taking. As you'll see, everything will be defined in a frame, and so we'll treat time and space as on independent footing, which is useful because, as is standard in this literature, we're going to Fourier transform only the spatial components and leave time as time. Okay. So I just want to show what the action looks like, and then we'll spend the rest of the talk kind of digging into what this means. So if we start with just standard massive scalar phi to the fourth theory in gravitational background, or just in curved space, actually, this could be in just fixed de Sitter. We all know how to do this, right? You just promote your derivatives to covariant derivatives and minus g, and so expressed with the sort of standard FRW-like rewriting this just using a scale factor, you get a full theory action that looks like this. Okay, this is totally standard. And what we're going to find is that we can integrate out the hard mode systematically to arrive at what we call the soft de Sitter effective theory. This name was actually provided by Matt Baumgart and Raman Sundram in a recent paper of theirs that's quite closely related, where they sort of did a beautiful calculation that I would argue is the old-fashioned QCD perturbation theory approach to what we're doing here. So these are very nice complementary approaches. And at the end, they said, well, it would sure be nice if we had a systematic effective theory description of this that we'll tentatively call the soft de Sitter effective theory. And so when Dan and I saw that, we were like, oh, well, that's what we've been working on. And they were gracious enough to let us take their name. The soft de Sitter effective theory is built out of slightly different degrees of freedom, which I'll define in just a moment. But the kinetic term is linear in time. Okay, so we're going to need these 2 degrees of freedom, phi plus and phi minus, which for anyone who's familiar with this literature will recognize as the growing and the decaying modes that come from just solving the free equation here. And then they're going to be organized in this tower of operators, which are going to come with well-defined power counting. And one way to, a naive way of just tracking the power counting is just it counts powers of A, okay? So that's not exactly right. I'll be more precise in a moment, but because of the power counting plus symmetries, essentially power counting just tells you where to put the A's. And again, that's super useful because when you do these calculations in the full theory, there's A dependence, which appears from taking commutators and so on. In curved space, the canonical commutation relations also get dressed by factors of the metric. And so you get A's from commutators. It's quite obscure where all the A's come from. And you sort of just don't know until you get to the end what your time dependence looks like. And so that's one of the real conceptual advantages here. All of our time dependence is going to be explicit and related to power counting. Okay, so this is kind of the punchline. These are the 4 main applications that we worked out in our paper. So I want to tell you the application, and then I want to give you a slogan so that maybe you'll remember 1 or 2 of these. The first is we're able to calculate correlators for massive scalar fields in the long wavelength limit. And I've already kind of told you the punchline here. What's going to happen is that all these modes decay exponentially fast. And that is mirrored in the operator structure it's going to turn out that the only operators we can write down consistent with our power counting are irrelevant operators. Irrelevant operators are suppressed by powers of 1 over a. 1 over a goes exponentially fast, dies off exponentially fast. And so we say physics beyond the horizon is irrelevant in the massive case. Okay. And we'll be able to see that work out exactly. Then what's actually been kind of a hot topic lately, there's been a number of papers, there's actually one just a few days ago, has been understanding the massless limit where Starobinski's stochastic inflation formalism applies. And there's lots of different approaches that all give the same description. And so we have our own. For us, you don't have to be clever. You use exactly the same techniques that applied in this case to the massive scalar fields. You just, because the power counting is going to depend on the mass, the power counting changes. And we go from all possible interactions being irrelevant to some of them being marginal. In fact, in the exactly massless limit, there's an infinite tower of marginal operators that you now have to resum using RG because they can mix. They all have the same operator dimension. And so it's that RG equation that is Starobinski's stochastic inflation, okay? And the connection between RG and stochastic inflation is something that's been pointed out before in the literature, but here it's there in many of those papers, you had to be clever. Here, I really want to emphasize that once you have the EFT, you just follow the absolute standard techniques. You just open Peskin and Schroeder and calculate, okay? Then, so both of these cases were in fixed de Sitter. And so we also investigated some applications when gravity becomes dynamical. So that's 3 and 4 here. So with 3, we can also apply this to understand metric fluctuations during inflation, right? So that's the application that pertains to the cartoon I was talking about at the beginning of the talk, right? The story we all learn about modes freezing out outside the horizon. And actually, Dan and Daniel Bauman, some number of years ago, I forget exactly when that paper came out, proved that the superhorizon modes do actually freeze out to all orders in perturbation theory using the NN formalism. But Dan is the first one to tell you that that calculation is horrible. They had to work extremely hard, and it wasn't at all clear where the A's appeared. This is a great example calculation where it wasn't at all clear where the various factors of the scale factor appeared until the very end of the calculation. And so they understood this sort of brute force diagrammatically, and it's going to turn out in the EFT, it's just a consequence of power counting. So literally, once you write down the EFT, you immediately see that there are no relevant or marginal operators you can write down. And so everything is suppressed by the scale factor, and the superhorizon modes freeze out when gravity is dynamical. Okay, so that was very satisfying, is that we have a really simple argument that works to all orders that, of course, agrees with the literature, which also proved this, but doesn't require you to work very hard. Okay, you can see it intuitively. And again, that's one of the benefits of EFT, right? If it's really working for you, what it does is it provides you with intuition for why, you know, big, profound physical results like this one are true. Okay. And then the final application, it's probably a little overstating it to call it an application at this point, but we can mutter a few words about eternal inflation. And in particular, what we find is that in the internally inflating regime, now a tower of relevant operators appear. And so it tells you that there's a novel phase that you actually have to solve for the dynamics non-perturbatively to incorporate those relevant operators. Now, we don't know how to do that yet. It's something on our list of things to be thinking about. We're kind of poking at it, but we can at least see why eternal inflation is so different from the point of view of the EFT. Okay. Great. So where should we start? Well, we need a scale, right? EFT is all about some kind of expansion in terms of a ratio of scales. And in DS, there's an obvious scale, which is the inverse co-moving horizon. So for us, the UV scale is going to be set by AH, okay? Now, this is a little funny because of course, A depends on time. We're not used to our scales being time dependent, okay? So that's one of the odd features here, but when you formulate the theory using this as your UV cutoff, if you like, you can think of it as a fixed time slice. And then from that time slice, everything tells you how to time evolve forward. It appears we're getting the right answer. And then we want to take the long wavelength limit. So here's our ratio of scales, okay? We're taking momentum modes much, much smaller than AH. That's the long wavelength limit of de Sitter. And the power counting, we use the standard terminology of a little lambda for power counting, is simply given by K over AH, okay? So this is, for example, what you do in heavy quark effective theory, right? It's an expansion in terms of inverse powers of the heavy mass. And so it's a small momentum over heavy mass expansion that defines a power counting in exactly the same way we have here. So let's go back to this picture I had on my title slide. So hopefully this makes a lot more sense if it was perhaps a little bit obscure then, right? We have these UV modes where the power counting is large. So those are the modes we're going to integrate out, okay? And we have these SdSET modes where the power counting is a small parameter. And so we can hope to do a convergent Taylor expansion in this regime. And these are the modes whose wavelength is much larger than the inverse co-moving horizon scale, okay? And just briefly, I want to mention, because there's, of course, a very famous EFT of inflation, that EFT sort of lives in a different regime. And so there's an intermediate regime where the EFT of inflation applies. If you're unfamiliar with it, you can kind of think about it as the Goldstone equivalence limit for gravity in a quasi-de Sitter background. And so the EFT of inflation is really about the Goldstone boson there. We're interested in dynamics at much lower scales, okay? So this is a different effective theory than the EFT of inflation. Okay, so I gave this conceptual and practical reasons. And so I am just dressing this up with a little bit more technical language, but I'll go through this very quickly, right? We isolate propagating degrees of freedom. Those will be our phi plus and phi minus fields. We write down a quadratic action that tells us the dynamics. Then we expose symmetries, okay? Our power counting is just going to be dimensional analysis in terms of K over AH. We're going to be able to regulate integrals without breaking any symmetries using a variant of dimensional regularization. And we're going to apply the RG to some full theory IR logarithms. Okay, so the starting point, and this is kind of an outline, okay? So the starting point is what are the degrees of freedom? So we're going to factorize into hard and soft modes. Again, in very close analogy with what's done in heavy quark effective theory or modern continuum EFTs. SCET is another example where you do this, soft collinear effective theory. So you just say the full theory field has a soft component and a hard component, okay? And if you can find the right power counting to separate soft from hard, then the point is that they factorize, you can integrate out the hard stuff, leaving you with a local Lagrangian for the soft stuff, okay? And if you succeed, then your observables will be organized order by order in your power counting parameter. So your power counting gives you, essentially you get logs of power counting, and then you just get power corrections, which are a Taylor expansion in terms of power counting. So let's isolate the soft modes. Okay, we have the DS metric. I didn't mention it before, but I had snuck this notation in previously. It's just we rescale time by a factor of Hubble, where t is the proper time. And what that does is it just brings out essentially a factor of Hubble out front, but it gives us, it's a change, if you like, it's kind of like natural units, it's a change of the dimensions. And when we work with this t underline object, all of the dimensional analysis is completely manifest. Okay, so it's a trivial thing, but it makes the figuring out where powers of something dimensionful, in this case h, appear. Okay, and in technical expressions, which will probably get flashed by very quickly, occasionally conformal time will appear, which is just a rewriting of time. But when you're actually doing the calculations, it's often convenient to do the integrals using conformal time. Here's a scalar field in static de Sitter. Sorry, it doesn't have to be static. This is just a scalar field in de Sitter, okay, where we've used the scale factor defined here, right? And we've just taken the action I wrote a few slides ago and found the equations of motion, okay, for a free scalar. And all the soft limit is setting k to 0. So when you set k to 0, you can solve this differential equation. It's almost trivial. And what you find are two solutions, okay? This is one place where I'll apologize for notation. I will either use nu, which can take a positive or a negative value and depends on the mass this way, or an alpha and beta, just depending on what's convenient. It's the same thing. Alpha and beta are constrained to be 3 because of the 3 spatial dimensions. But you should think of nu or alpha and beta as just proxies for the fundamental mass of the UV particle, okay? So we're going to, in the EFT, M is not going to appear anywhere, kind of by magic. It appears at intermediate steps, but in the final action, once you've used all the tricks to simplify it fully, M disappears, or anything that looks like a mass. And all the dependence of the UV mass will be encoded in this nu, okay? Now, here's one of our tricks, is we take the naive soft field and we rewrite it as this explicit time dependence multiplied by this var phi. So I'll distinguish phis, which are the soft modes of the full theory, from var phis, which are going to be the propagating modes of the EFT. And all we are doing here is pulling out the leading order time dependence. But in doing so, we're going to make all of the time dependence much more manifest. Okay, so I've already said this. We have these growing modes and decaying modes. The correlators of interest at the future horizon and infinity are all correlators of the growing mode. This terminology is standard. It's a little bit unfortunate. The growing modes also decay. They just decay slower than the decaying modes, okay? So when you take the long wavelength limit, the only things that survive or that have a chance of surviving are the growing modes, okay? And those are the correlators that are relevant for cosmology, so that's what we'll focus on here.
Sorry, can I ask a quick question here?
Yes, please.
Yeah, if you go back to your previous slide.
Yeah.
So is K 3 momenta? So I'm just asking because is it obvious that the K square over H square is always smaller than M square over H square?
Great. Yes, K is 3 momentum.
Oh,
right?
3
so
momentum.
I have separated time and space already here, right? Because I have explicit time derivatives. Right. And so, yeah, so we are typically going to Fourier transform the spatial components. And so all Ks will be 3 vector Ks, and we're going to stick with time as time. Okay, we're not going to Fourier transform time.
Okay, thanks.
Yeah. Yeah, so this is literally, this prefactor is literally the power counting expansion parameter. Excellent. Okay, so those are the degrees of freedom. Doing okay on time. Great. So one of the novel things about this EFT is that we have to add an additional component, if you like, at matching, which is that there are stochastic initial conditions for the field. Okay. So there are a few ways to think about this. Maybe not go to that slide yet. So there are a few ways to think about this. One is that we have a horizon. You can think of it as a physical boundary. And so not only do we need to talk about what are the fields that survive beyond the horizon, but we also, at least in principle, have the ability to set up initial conditions at that boundary. And it's going to turn out that to get the physics right, we actually are forced to include stochastic initial conditions. And so let me tell you a little bit about where those come from. I quite like this. It's not, I wouldn't argue at all that it's a new calculation, although we kind of synthesize it in a way that I think is really clear and beautiful. But this is the most detailed example I've seen of explaining the cartoon that the quantum fluctuations of the inflaton become the classical initial conditions that seed structure. Okay, so let me just quickly race through how this works. You quantize your field in the full theory using the standard canonical quantization. I just taught this in my QFT course last week. Okay, so you just expand in terms of creation and annihilation operators. The only difference with de Sitter is that instead of the mode functions being plane waves, there are these kind of horrible Henkel function dependent objects here. Okay, so the Bunch-Davies assumption that essentially, which is an assumption about the vacuum state of the full theory, gives you these solutions in de Sitter space. But the creation and annihilation operators satisfy the standard commutation relations that we're all familiar with, that I was just teaching last week. Okay, so now we can just take the soft limit of these objects here, right? Just Taylor expand. And what we find is that our modes that we identified before appear. So we have something proportional to AH to the minus alpha, something proportional to AH to the minus beta. There's a linear combination of A and A dagger that appear. We'll call that A tilde and B tilde. And in that expansion, these prefactors give us the classic scale invariant spectrum, at least in the massless limit when alpha goes to 0, right? This is just literally the 1 over k cubed scale invariant spectrum you get for the 2-point function, okay? So we can just identify these A tilde and B tilde objects. They satisfy the following excitation v vacuum is non-trivial, and in particular tells you that these objects A tilde and B tilde act as just stochastic random variables. Okay, so they are correlated in this sense, but there's no quantumness. Okay, so it's a fancy way of saying what this is it's just a Bogoliubov transformation. We're basically taking the UV creation and annihilation operators and transforming them to the horizon. And in doing that, they become classical stochastic initial conditions. Okay, so when doing calculations, there are two possible contributions you can get. One is you can just have...
Sorry, what happened to the canonical commutation relations of the fields?
Sorry, for which fields?
Well, the set of operators you've written there are the mode expansion of the field. The field had canonical commutation relations, which had a non-zero right-hand side.
That's right.
So, so how can you have the equations pointed to by the arrows and still have the fields obeying canonical commutation relations?
Yeah. So these are the mode. If you like, you can think of these as the modes for the. These are the modes for the EFT fields, and they're going to satisfy a different set of commutation relations. So when I write the action, I'll show you that maybe if I can just postpone a slide or two. When I write the action, it's very clear who the conjugate momentum to phi plus is. It's just phi minus, and then there's a non-trivial commutator between phi plus and phi minus that captures the quantumness of the long wavelength modes. So
it's commutation relations between the A's and the B's that are reflecting that. Is that what I'm hearing?
That's right. Exactly.
Okay.
Yeah. Thank you.
All right. Thank you.
Great. Yeah. So we identify operators. And so these are our EFT modes. They have the scale invariant, or depending on the mass, but the potentially scale invariant power spectrum as their as the coefficient here. And yeah, and well, here's the 2-point function for the initial conditions. Okay. Great. So now let's get into the quantum theory of these long wavelength modes. So I've said this a lot already. Here's our degrees of freedom. Here's our power counting. Our symmetries, we're going to just inherit space-time symmetry from ds. Okay, so that's going to look pretty similar to the full theory space-time symmetries. We're also going to have a reparameterization symmetry that's a lot like what happens in heavy quark effective theory. Basically, the fact that we split the full theory mode into a number of hard and then a number of soft modes means that there's some ambiguity in the way we did that split, which gives us the ability to reshuffle, and that's a reparameterization invariance that's going to be very useful for constraining the form of the action. And then, as we've already talked about, we have these initial conditions. Okay, so other than the initial conditions, everything we're doing here has a very close analogy with heavy quark effective theory. And in fact, the way this project worked was Dan would show me how to do a calculation in the full theory. We would Taylor expand it, and then we would stare at it and try to figure out what is the analogy with heavy quark effective theory. And that turned out to be extremely fruitful. Every time we got confused, we said, wait, what's the analogy with heavy quark theory? And that always led us down the right path. Eventually, in hindsight, we should have just started there. And in particular, once you know the power counting, which is an input, right? We impose this on the effective theory. We say it power counts this way, and you enforce that the action power counts as order 1. Then you, just like the way we define the dimensions of fields in normal quantum field theory, right? You say, the dimension, the action is dimensionless. You know how space and time and that tells you what your fields carry. The same thing happens here. I'm not going to go through the argument. It's very simple. But what you find is, in particular, that phi plus scales like lambda to the alpha, phi minus scales like lambda to the beta, which exactly maps onto the rule I told you. If you go back, let me just show, say, yeah, for example, here, right, it's this scaling with 1 over a to the minus alpha and 1 over a to the minus beta in front of each of these, which is exactly reflected in the power counting. The space-time symmetries manifest as follows. So there's just a transformation you can do here that is essentially just coming from the fundamental boosts and rotations. And there are additional isometry transformations when we're working with static de Sitter. When gravity is dynamical, you don't have those isometries anymore. And here's the reparameterization invariance that I mentioned. It's basically you're just able to reshuffle phi plus and phi minus into each other as long as you preserve power counting. And so you can transform these into each other using this parameter epsilon. This has a typo. There should be some epsilon dependence here, sorry. Okay. So then, again, in analogy with heavy quark theory, we take our mode expansion, we substitute it into our full theory action, and we just try to reduce. We use the equations of motion, we use integration by parts, we apply power counting, okay? And where we get is to this equation here. So there's still a lot of terms here. In particular, what I want to point out, because I want to go into in a little bit of detail, are there's some phi dot squared terms, and there's also this mixed phi dot plus phi dot minus term, okay? So first, we're going to drop any subleading terms in terms of power counting, so that kills these two terms. You could take my word for it. It's just the range of the new parameter. And we can integrate by parts, and we can do the following field redefinition on phi minus. One of the nice things about this effective theory is that because we're only interested in correlators of phi plus, we're allowed to do whatever we want with phi minus that makes life easy. And so we will often be able to find field redefinitions using phi minus that get rid of leading behavior in terms of phi plus, again, as kind of standard in effective theory, and just makes life easier, pushes things off to higher orders. And so this is exactly the kind of field redefinition we can do. By the way, we're calculating correlators here, so we're not guaranteed that, in fact, it is not true that they're unchanged by field redefinitions. So we're not allowed to play these games with phi plus, okay? But again, because we're calculating everything in terms of phi minus, we're fine. Okay, so again, it's if you're interested in details, we probably put too much detail in the paper, but it's all laid out, all these steps, and we get here, okay? So we have something that looks very simple. The only confusing thing is we have this term with two time derivatives, okay? And thankfully, Weinberg, in his original paper on this subject, he also encountered this two time derivative term. And he provides a beautiful argument that this is subleading, okay? And the point is that if you, basically it's a question of degree of freedom counting. So what we've done is we've taken a quadratic action in terms of one real field, we've reduced it to a first order action in terms of two real degrees of freedom. And so if this is the kinetic term, then as I'll show in the next slide, it is systematically appropriate to treat this two time derivative term as being power suppressed, okay? So that's a self-consistent assumption, and I just want to give you a little bit of insight, because that's the sort of one non-trivial, like real physics step in going from the awful Lagrangian you get naively when you just plug in to the really beautiful final result. So to see that, let's assume it's true, okay? So that reduces us to, this is the free soft de Sitter effective theory, okay, to order lambda squared. Note I've included the leading, or the first sub-leading term in terms of power counting here. So this is the kinetic term. And you can just solve this. So it tells you that the phi plus time derivative is 0 to leading order, which is great. That was by construction, right? We stripped off the time dependence when we defined these fields. But it's nice to see that after all these manipulations, that's still correct. Okay, so that had to be true. And then it gets corrections proportional to power counting or inverse powers of the scale factor, okay? And this tells you that time derivatives are power suppressed. So every time you apply a time derivative, you get an extra factor of lambda squared. And so that's essentially an effective field theory way of making Weinberg's argument from his paper.
Sorry, can I ask a question there?
Yeah,
so is this time derivative is with respect to t underline or without it? So
yeah, t, that's right, t underline. Yeah, this, and there's not too many of these typeset equations, but this like fancy t is the t underline.
Right. So my question is that you assign the time to be lambda to the 0, among other things.
Mm-hmm.
And then x to be scaled as 1 over lambda.
Yeah, that's right.
So then how is this assignment of power counting consistent with the result you just found?
Oh, yes. So so what that's so the fact that time derivatives scale as order 1 is the statement that that the leading power solution is the constant. Okay. So this is, if you like, the sub-leading correction, right?
Uh-huh.
Does that make sense?
Kind of. Yeah, I'll think more about it and then we can chat later.
Yeah, sounds good.
Thanks.
Yeah. Okay. Oh wow, I'm about out of time. I'm going to skip this. In the paper, we provide a one loop argument that the integrating out the heavy mode leads to a local action. The punchline is just because of the structure of the interactions, you only get contributions starting at one loop order. So we do a one loop estimate and show that you get local contributions from integrating out heavy fields. Okay, this is the last important conceptual thing about the EFT. Naively, you would think that this is the leading interaction, just some polynomial in terms of phi plus. But again, because we can do these field redefinitions on phi minus, it turns out we can remove any polynomial in terms of phi plus and shuffle it into higher order terms. And so the leading interactions always have some non-zero power of phi minus, okay? And that's critical to the success of all the power counting arguments. So we now have well-defined power counting just depending on the number of factors of phi plus and phi minus, right? We can do the same standard organization into relevant, marginal, and irrelevant operators, okay? So that's it. That's all the hard work. Now you just calculate. You just follow the standard rules. Great. So here I'm just making the argument that as promised in the massive case, all possible interactions are irrelevant. Okay, and again, it's just it just follows from these kind of arguments. When alpha is non-zero and beta is non-zero, then all these operators are irrelevant operators. As you take the mass of the fundamental field to zero, alpha goes to zero, and so now you can start to get some operators be relevant. And as alpha is strictly zero, you get an infinite power of relevant operators that can all mix under RG. Right. Yeah, sorry, I'm running out of time, so I'm just trying to decide what to show you. Basically, we have a trick to deal with scaleless integrals that we call dynamical dim-reg. It amounts to doing an analytic continuation in alpha. It turns out when you do these in perturbation theory calculations, you get numerators that both scale with, and so the dim-reg approach to regulate these integrals fails because they diverge in all dimensions. And so, but because we can trace the alpha dependence as giving us this d-dependence here, or being related to it, it comes from expanding those Hankel functions, which depended on alpha. If we just take alpha a little bit away from the physical solution, do the calculation for that unphysical choice, and then analytically continue back, that regulates integrals and looks exactly like dim-reg. And we call it dynamical dim-reg because it's changing the time dependence of the field by changing the value of alpha. Okay. So Seth, I have 5 minutes.
We started a bit late, so 10, if okay. That works.
Yeah, I will. I'll definitely end before 10, and then, like I said, I'm happy to stick around and show more of these slides or chat about anything. Okay. So I'm not going to go into this. I think the most interesting thing I'll show you is the stochastic inflation application. So here I just want to say in our paper, we match a variety of calculations performed last year by Dan and his student in the full theory up to 2 loops. So we look at correlators of composite operators with massive scalar fields, and we can calculate anomalous dimensions in the EFT, and we get exactly the anomalous dimensions that Dan and Akhil found in their paper. So this was well, this was big for us because this really told us that we had things working. We were getting the factors of 2. Okay. So once you've established that the EFT is working in the sort of trivial case where everything is irrelevant, then you can move to ask questions where the dynamics becomes more interesting, where the interaction structure in particular becomes more interesting. And so as you take the massless limit, I've said this many times now, your alpha goes to 0. And all of these operators with 1 power of phi minus and n powers of phi plus scale like this. And as alpha goes to 0, those are all order 1. So that's our tower of marginal interactions. And the equation of motion, which is given here, simply tells you that the relates the time derivative of phi to this polynomial. Okay, so we'll use that in a moment. So in order to investigate the Starobinsky approach to stochastic inflation, we need to look at composite operators That's because if you like, what Starobinsky really calculated was a probability distribution of the RMS value of the scalar field. So we really need to look at correlators of phi squared, right? If you just look at correlators of phi, you just get the standard problem that you get phi in the plus direction, canceling phi in the minus direction. So you should get 0 on average. Okay. So you really need to look at phi squared. So let's take this theory and just evaluate the RGE for a composite operator of the form phi plus to the n. Again, in the massless limit, using the same argument as before, these all scale as order 1. So these operators are all going to mix under RG. So if you contract any two legs, the way these rules work, you start with some correlation function that includes the operator On. You contract two legs, you go On minus 2. There's some combinatoric factors. And then I think I flashed the C alpha thing on one slide. This is just the coefficient of the stochastic initial conditions. And this comes from actually using those initial conditions when you do the contraction. Okay, so this is the nearly scale invariant power spectrum here in the denominator. And the contraction just gives us an integral over this unknown momentum. Now, this integral is scaleless. And since we're using dimreg, it vanishes because there's no scale. So again, we'll follow our HQAT forefathers and use the standard tricks of isolating the UV divergences in scaleless integrals. We'll introduce some IR scale essentially at random. It doesn't matter how you do this because we only care about isolating the UV divergence. When we do that, we can evaluate this integral. And as promised, we get something that looks exactly like dimreg, where we've traded epsilons for alphas. Okay, so as we take alpha to 0, we get a 1 over alpha divergence. We get an Euler-Macroni constant, and we get an accompanying log of AH divided by the scale factor, divided by this IR scale. Okay, and it's, if you like, it's this log that now looks like a UV log from the point of view of the EFT that we can sum using RG. So in this DS literature, the RG goes under the name of dynamical RG. That's because, you know, one way to think about this is you're summing logs that are associated with this divergence, right? But those logs always have factors of A in them. And so you're, if you like, when you're resumming with respect to some unphysical scale, you can just do a simple change of variables to rewrite that as a resummation in time. And so in this literature, that goes under the name dynamical RG. And so let's just follow our nose, just do RG. We're going to take a time derivative of this composite operator, and we get two contributions. This one, the first term here, is from the equations of motion, right? So that's literally just applying the time derivative using the equations of motion, you know, but appropriate for the composite operators. And this term is just what we calculated in the last slide. That's the quantum evolution, okay? So this is the sort of quantum piece of Starobinsky. Starobinsky derived this by bringing modes in from the horizon. So he was looking at modes that were near the horizon, and essentially this term is taking into account the physics that you're constantly integrating in more and more modes as you time evolve. This is just the classical piece, which is determined by the potential, okay? So if you like, this is the rolling, and this is the quantum fluctuations, okay? And that, again, all of those interpretations are completely standard. That's the story that practitioners tell when they talk about this. For us, it just falls out essentially for free, okay? And this is equivalent to a Fokker-Planck equation if you want to compute the dynamics of this scalar field. Matt and Raman have a very nice derivation going from, so they derive the same RG, so they so we didn't bother repeating that. You can go check out their nice derivation there. So great. Yeah, so what's really nice about this and why this is a hot topic currently is because there's a lot of different approaches which are trying to more formally derive Starobinsky's equations that govern the dynamics of stochastic inflation systematically, so we can add corrections. And so that's actually the most active area of progress we're making right now, with Dan and Akil, who I mentioned, and a postdoc at UCSD. We're actually trying to calculate in just lambda phi to the fourth theory the next order corrections to this equation. So that's in progress, so stay tuned. In some number of months, we'll be putting out a paper where we're going to claim to at least understand the next leading order corrections to this equation. I'm not going to take the time now to talk about the dynamical gravity examples, but the short answer is just the symmetries change a little bit, and because of that, basically you have an extra shift symmetry that governs the operator structure, and that because of that shift symmetry, the only operators you can write down are power suppressed. Okay, so that's what I'm saying here. You might think you could write polynomials, but they violate the shift symmetry. So you always have derivatives. Derivatives are always suppressed by AH. And so any non-trivial correlation functions among these modes in dynamical gravity only get power suppressed contributions. So they vanish as you take time to infinity. And that's the argument that was given at tree level in these very famous papers, and then proven by Dan, Daniel, and their collaborator, and also sort of at the same time proven by Leonardo and Matthias to all orders. Great. And then I had already told you that little story about eternal inflation. So the summary, if that I've convinced you that we have a systematic approach, and I've at least told you that there are many non-trivial calculations that involve factors of 2 in multiple loops that agree with the literature. And so, you know, it's effective field theory. You can never prove that it works, but in practice, we have not found any problems yet. And we're working on this new higher order calculation that I think will also be a very nice demonstration of this lowercase f fact. And I really want to emphasize something that's awesome about effective field theory, something that really drew me into the subject, is that when it doesn't work, it just doesn't work. So you get spurious IR logarithms that don't cancel when you do matching. There's all kinds of non-trivial consistency tests within the theoretical framework itself. And so it's not just that it matches some random calculation in the literature, but it's that we can systematically separate these modes and that we're getting something that makes sense. Okay, so that very fact, I think, gives us a lot of faith in the approach, and we're working to scaffold from where we are now. Okay, so my real summary is here. This is the same slide I showed before, so I'll just leave it up with all my slogans. Yeah, so you can go tell your friends that now you know physics beyond the horizon is irrelevant. You know how to think about stochastic inflation. It's just the fact that a tower of operators are becoming marginal in the massless limit. You can resum them with RG. You know why modes freeze out outside the horizon during inflation. It's just power counting. Super horizon modes are power suppressed, or excuse me, interactions between super horizon modes are power suppressed. And we have a little bit of insight, at least, into why eternal inflation is interesting. Now there are relevant operators that appear, and so we really need to rethink the way we solve the theory. Okay, thank you so much for the invitation and for your attention.
Thanks, Tim. That was fantastic. Let's unmute ourselves and clap, as is customary.
Thank you.
Are there any, maybe a quick question or two before we take a few-minute dance break and then come back for more extended discussion?
Yeah, I have a question. Because I have to leave for office
please,
hours.
Go ahead.
One of the reasons I thought people use the in formalism for these sorts of problems is that the sorts of fluctuations you're worried about basically correspond to secular growth of fluctuations that then freeze out and become classical.
Mm-hmm.
And so, so the infrared divergences are just the production of fluctuations in different horizon-sized bubbles that are, stochastically decorrelated from one another.
Mm-hmm.
So here, if you're not doing that sort of in informalism, where did those sorts of things appear and how are they accounted for in what you do?
Very good. Sorry, that's my fault that was unclear. Everything we're doing is still using the in informalism. So so all we're doing is calculating using these var phi plus fields, but always then using the Weinberg formulation of in informalism in terms of commutators. And I didn't show it. I told you I would, and then I didn't show, I think, but the canonical commutator between phi plus and phi minus is non-trivial. And so that gives you the non-trivial commutator that gives you the quantum corrections in calculations.
Okay.
Yeah. And another thing that you said that I think is clear in this formalism is that we are treating these as classical. There's a better way to get there, in the sense that this sort of, where do I have it? This leading order equation of motion is trivial, and so so we really, at some level, the trick is that we know what the classical time evolution is, and so we might as well just write that explicitly, and then we have a trivial evolution at the classical level for these objects, and then we order in the counting as well.
Great. Cool. Why don't we, I'll pause the recording, stop the recording, and we can take a couple minute